Hey everybody, in the second part of this lecture, we dive deeper into understanding confusion matrices. Each row in a confusion matrix represents an actual or true class. And we do have two cases here because we have a binary classification problem, negative and positive. We can think of these as yes and no or success and failure, but for now we focus on negative and positive. And similarly, each column here represents a predicted class or predicted label, and we have negative and positive. Therefore, we end up with four possibilities here, and the ones on the main diagonal refer to correct predictions. So in particular, if we have true class negative and predicted class negative, that's a true negative, and we can have true positive. But the two types of misclassifications that we have can be divided into false positives and false negatives. So false positives, it means that the true class was negative, but we predicted the class label to be positive, and therefore this is a false positive. And similarly, we have false negative. In many cases, we can just plot the confusion matrix and report this as the performance metric of our classifier. But it is also very helpful to be able to extract some interesting metrics from these confusion metrics so that we can better communicate the performance of our classifier. And in order to do this, let's start with what we call as precision. So what is precision? I like to show these arrows because these things really make this easier to understand. So precision means that we're going to look at true positives over true positive plus false positives. So what this means is that among all the data points that they're predicted to be positive, what percent of them are actually positives, which means that we are very sensitive to the number of false positives. So hopefully if this number is close to 0, we get precision close to 1. On the other hand, we have something called recall. Recall also is called sensitivity in some textbooks and literature. And this is kind of like what we have in this part, where it is defined as being the true positives over true positive plus false negative. So what does this mean? This means that among all the data points that are actually positives, what percentage of them are predicted to be positive? Which means that here we are very careful about the number of false negatives. And this thing is also called true positive rate, right? Because it's true positive over true positive plus false negative. Since we have true positive rate, now we can define true negative rate, which is the third metric that we have here. And this is sometimes referred to also as specificity, which is the number of true negatives over true negatives plus false positives. Therefore, in general, it is common to either report precision and recall scores or true negative rate and true positive rate. So the nice thing is that in the example that we just had with the MNIST data set, and we had this confusion matrix that we use confusion matrix display from scikit-learn.metrics, we can plot this to know exactly the number of true negatives, true positives, and false negatives. Or we can also at the same time find these precision and recall scores. And you can see that here from scikit-learn.metrics, we have precision score, and then we have recall score. And it's very easy because you just have to provide the true labels and predicted labels, and these functions are able to calculate these numbers. So here, for example, we know that the precision of this classifier is significantly lower than the recall, right? So this means that one issue that we have here is that the number of false positives, right, because that's what precision is measuring, is relatively high compared to the number of true positives. And we can see here this too, right? So if we compare 401 to 785, that seems to be a pretty significant number, right? Whereas if we look at recall, which is 785 over 785 plus 107, this is significantly a better score because this number of false negatives is here smaller. So that's why you can do a lot of discussion on precision, recall, and their implications. But what is important is that what we have done right now, we only have one precision score, one recall score. And in many cases, we want to be able to combine them together and give one number. And one way to do this is using F1 score, which is the harmonic mean, not arithmetic mean, of precision and recall. And harmonic mean is defined for two numbers as 2 over 1 over the first one plus 1 over the second one. You can simplify this and you can see that this is equivalent to 2 times precision times recall over precision plus recall. And something to keep in mind is that precision recall F1 scores, they're all from 0 to 1, and closer to 1 is better. So higher is a better score. But something that we need to keep in mind is that so far, when we have a threshold at 50% to define positive and negative labels, then we end up with one value for precision and one value for recall. But something that we can always do is to consider different decision boundaries or different thresholds for our classification. This goes back to the discussion that we had before, and I think the easiest way to understand this is this plot of decision boundary in 2D. So what you do when you use .predict, when you're using a probabilistic classifier, you use this 0.5 line as a way to distinguish between the two classes. But as we said, we can always move this line to the right or left if we change the probability, meaning that saying that, well, if the probability that a data point belongs to the positive class is at least 0.75, then it's positive, and if it's below 0.75, then it's negative. And obviously, this will give us a different precision and recall score than the one when we use this dashed black line here. So that's the idea behind precision and recall, that we can change the threshold that we use for distinguishing between positive and negative classes, and we can use these to identify trade-offs between the precision and recall score. And the curve that we get is called precision recall curve. Or we can do this using precision recall display in scikit-learn. So let's do this first. So in this case, something that is very important is that you do not need to provide, or you should not provide, just the predicted labels, because we do need to have access to those probability scores. So you can see that in this case, we use from estimator instead of from predictions. You provide your estimator, your testing data, the inputs, and the labels for those. So this means that in the background, we are going to consider different thresholds or different decision boundaries and use those to find different values of probability, values of precision and recall. So here you can see this curve that we have here, and you can see that on the y-axis we have precision value, on the x-axis we have recall, and this red circle here is the value that we got previously when we set the threshold to be at 0.5, which is the default threshold. So you can see that these are the values we got before, but obviously if you want to have precision values closer to 1, we can do that. But here's the trade-off. Probably then the recall score is going to be very close to 0, which is not great, right? So this means that if you want, yeah, we can have a classifier that doesn't have false positives, but then what it means is that most likely we are never predicting anything as positive, so therefore false positives are non-existent, right? So that's kind of like these extreme values. But usually we want to be somewhere where we have a reasonable value of precision and reasonable value of recall. And here we have this discussion on this too, right? So if you raise the threshold, and by threshold here, you can think of that as like that probability score. The reason we call this threshold is that because there's this one-to-one correspondence between probabilities and logits, what we had before sigmoid function. So that's why, we can really think of this as probabilities or real valued numbers that they go inside logistic function, but they're, technically the same because there's a nice one-to-one correspondence between inputs and outputs of the logistic function. But if we raise the threshold, which means that we are raising the probability, then this means that we're going to increase the precision score because then we will have fewer and fewer false positives, right? And similarly, if we reduce or lower the threshold, then means that we're going to increase the recall score because we are going to decrease our false negatives because it becomes more difficult to label something as negative incorrectly, right? So there's this trade-off between the number of false positives and false negatives, and in many cases we cannot decrease both of them at the same time if especially we have class overlap and so on. Another thing that we can do, which is similar to the precision recall curve, is the ROC curve. And in this case, what we do is we plot the true positive rate, or TPR, and we know that this is called recall, if we recall, right? So this is the recall score, which is true positive rate. And we can do this against the false positive rate. And false positive rate is 1 minus true negative rate, right? So it's very kind of like a similar idea to the precision recall curve, except the fact that now here we really want to know the trade-offs between true positive rate and true negative rate, or better to say 1 minus true negative rate, right? But obviously these two things are very much connected. And this means that the top left corner of the plot is the ideal point because you want to have the true positive rate to be as close as possible to 1 and the false positive rate to be as close as possible to 0. And if I use scikit-learn to plot this, so you can see that this is very much like other things. You import ROC curve display. And then for your ROC curve display, you need to have the false positive rate and true positive rate. And in order to find these things, you can also use ROC curve from scikit-learn, and you provide the true outputs for your testing data and these scores that we get. And these scores are what coming from the decision function. So again, these are these thresholds that we really need here. So in this case, you can use this decision function method and pass this to this ROC curve. And in this case, you get false positive rates and true positive rates. And if you plot these, so you can see that how this ROC curve works, right? So this ROC curve, as I said, you ideally want this to be very sharp and get close to 1, while false positive rate is close to 0. That's like the ideal work. But you can see that in this case, obviously, that's not achievable. And we can get close to almost like 0.85 or so before the false positive rate increases to 0.05 or 0.1. But overall, still, this is a really good classifier. And one way to summarize this curve as a single number is this AUC, or area under the curve. And therefore, if this is exactly like a 90-degree here, which is the ideal scenario, then we get exactly 1. But in this case, you can see that that's not possible. So you get something close to 1, but not exactly 1. And still, that shows that this is a pretty good number. And again, this red circle that we have here is the case when we use 0.5 probability as the threshold to decide whether a class is positive or negative. And that's something that the only thing we need to really think about here is that for the recall score that we had before, now on the x-axis, we have false positive rate where you have to use this 1 minus recall score, right? So you have to make sure that you find actually the true positive rate and false positive rate. And that's how we find false positive rate in this case. But similar to the precision recall curve, we can change the threshold and get to different points of this curve. Something that is kind of mysterious in many online resources or even in some textbooks is that they claim that this diagonal line, this 45-degree line, right, that goes through 0, 0, and 1, is the ROC curve for a random classifier. And so obviously you want to be above this line because that should be kind of like your baseline or worst case performance, which is not super clear how this works. So that's why I added this theoretical analysis here to explain how this 45-degree line corresponds to a random classifier. So in order to do our theoretical analysis, we have to make some assumptions. So assume that there is a fraction of positive cases and a fraction of negative cases in your data set, right? So here we assume that we have n data points, the uppercase n. And so if we multiply x times n, that's the number of positive cases that we have. And x is obviously a number from 0 to 1. And now assume that you have a classifier that randomly assigns positive classes with probability rho. And we change this rho from 0 to 1. So we can have a classifier that with probability 0 assigns a positive class, which means that always provides negative labels, or vice versa, a classifier that always provides probability 1, which means that always the output target is, or predicted target is 1. So in this case, let's see if we can find the 4 quantities that we need to be able to find the ROC curve, meaning true positives, true negatives, false positives, and false negatives. So you can see that for true positives, right? So x times n is the number of true positives that we have, and the probability that we assign a positive class label is also rho. So this means that in this case, the number of true positives on average is x times n times rho. And the same thing you can say with false negatives, right? Because this means that these are the cases that they were true. So x times n, the number of true classes, true data points, or data points with true labels. And now we multiply these by 1 minus rho, which is the probability of assigning the negative class. So this means that now these are the number of false negatives. Similarly, for true negatives, we have to first find the number of negative cases and multiply this by the probability that the classifier produces something as a negative class. And for false positives, so these are actual negative data points or data points with negative labels that now they are labeled as positives. And so we have 1 minus x times n. So these are the number of data points with negative classes. And then we multiply by rho, which is the probability of assigning the positive class. So based on these, you can actually find your true positive rate and false positive rate. So true positive rate is true positive over true positive plus false negative. And the same thing with false positive rate. And if you do the math and simplify this, you can see that the true positive rate is equal to the false positive rate, and the answer is rho. So based on the value of rho, you get from here to this point, right? So this is kind of like the path that we take by changing this rho parameter, right? Meaning that in this case, if you're at these points, right? So we have true positive rate is equal to 1, which is great, but then false positive rate is also equal to 1, which is not so great, right? So that's something to keep in mind, that we want to avoid to be in these two extreme points, right? And hopefully we have a classifier that takes us to this corner here. The last question that we want to answer here is what if we have a classification problem with more than two classes? This is what we call it as the multinomial logistic regression. And it doesn't necessarily have to be logistic regression. It can be any classifier like SGD classifier here. And you can see that in this case, in order to show this, we are using the original training labels from this data set, meaning that we are not just constrained to that, digit 5 classifier that we had before. Here we have actually all 10 classes in this Y train. And we can probably even visualize this to just make sure that that's actually the case. So if I show you here, you can see that this Y train is the one that contains all 10 digits or categories. And the one that was only 5 or not was this Y train _5. So we are not using this one. We are using the original labels that we have here. So in this case, we have couple of ways to evaluate the accuracy of our classifier. For example, we can just use accuracy, which is the number of correct predictions over the total number of predictions or the total number of samples. But something that also works very well if we have, let's say, up to 10, 20 classes is using confusion metrics. And in this case, again, we can use from predictions, provide the actual labels and predicted labels. And you can see that if you use this heat map type visualization, we can easily see that, yeah, we are making some mistakes, but overall these diagonal terms are dominant. And we do have, for example, some problems, I would say, with digit 8, right? So you can see that a lot of images that are actually from class 2, 3, 4, 5, they were labeled as digit 8. So that's like one of the places that we have to work on if you want to improve this classifier. But some of the other metrics like precision recall, obviously they do not immediately extend to this case of multiple classes, although you can always find these values for like binary cases, meaning that let's say if you have like one versus the rest of classes and then take some average and so on. So there are options to manage these cases. But for the most part, my recommendation is that if you have like 10, maybe up to 20 classes, using confusion metrics is very helpful. You get a lot of information, especially if you use these heat maps. And that tells a lot about the quality of your classifier. So with this, we have covered decision boundaries, confusion matrices, precision recall curve, and ROC curve. And also now we know why this 45-degree line in ROC curve corresponds to a random classifier. So we do have a mathematical analysis of that. And I hope you found this video helpful.